Okay, here we are. It's the physics video lecture. psci 168, video lecture 40. And I'm going to pick up where we left off. We're talking about the laws of electricity and magnetism. I brought some demonstrations. Wish me luck. See what we can do today. And have some demonstrations off camera that I'll wheel in. So let's go ahead and kind of start that list we had last time. The laws of electricity and magnetism. And we often over here at physics, E and M. So what did we have? First of all, we can review electricity. And we know we have charge. Charge plus minus Q. We know that there is a force. And I'll just leave it at that, attraction and repulsion. Then we know there is energy. And we even have that formula work is equal to Q delta V, which brought the idea of voltage into play. And then we have current. Electric current I is equal to Q over T, or I could put delta Q over delta T, meaning pretty much the same thing. Current measured in amperes, delta V measured in volts. So we were on familiar ground there, and then we had power, I delta V. And with our basic concepts, we were able to calculate anything we wanted to know in terms of how much it costs and how much it takes to do something. Okay. So that was electricity. Magnetism I introduced the other day. And when you're talking about magnetism, you can start with bar magnets. Here was our bar magnet, for instance. We've got a magnet there. It's got a north and a south pole. So let's go ahead and draw a bar magnet. Encourage you guys to leave a lot more room. I'm just kind of compressing it here. So magnets, and the force with the magnet is that like poles repel and unlike poles attract. So we have a force, interaction. And if you have a force, you can think there's going to be energy involved as well. Same way we said force, and then we have work. Okay. So we had that, but what we're driving at now is the magnetic field. And I already named it the B field. I can put an arrow on top to point out that it's a vector. And the compass needle's pointing every which way we're pointing in the direction of that B field. So the B field of a dipole, which is what a basic magnet like that is, I'm going to draw. Once again, we have north, south. We can take a different color for our field lines. And the vector nature of this is as follows. If you put compass needles at one of these places, they are going to point in that direction of that line. And the formalism tells us that the field lines leave at the North Pole and they come back at the South Pole. So this one here, for example, would connect all the way, get rid of that, and leaving at the North Pole and returning at the South Pole. So I also encouraged you to look up things like this and print them out. You get some images in your book. And so we're talking about a dipole, magnetic field of a dipole. So that was electricity and magnetism, and we did not yet see a relation between the two. And that's where it's going to get really interesting. So they go together and they're going to be linked here on my third point. And that is that a magnetic field acts on an electric current. So if I take an electric current through a wire and hold it in a magnetic field, there will be a force on it. And I'm going to demonstrate that next. So magnetic, and I'm using this short form, just calling it B field for magnetic field. You guys will get used to that. Acts on an electric current. And I'll even get us a little picture here, first of all. So you'll notice that I've got these arrows leaving the North Pole. So suppose we have a North Pole. So suppose we have a North Pole and a South Pole. I'm going to separate these a bit. And a South Pole and a North Pole. So we set up two magnets like that. Then between these magnets, there is a very strong field. Okay. And if I put compass needles right between these magnets, they're going to line up straight, just like that. So the force on a wire, F is equal to I L cross D. Now this is a formalism you guys don't have to learn, okay? But you can have it in your notes for culture. Current times the length of a current element, a special kind of multiplication called the cross product, don't worry about it, times a magnetic field. So you can see what the force is made of. Current, length, magnetic field. Okay. Amperes, meters, magnetic field. We'll leave it at that. So suppose we have so suppose we have a wire that's going to say have a current. So I'm going to say the current is coming down like that. So this is the current that's in that. This is an actual wire. Okay, this red line is an actual wire. So what kind of a force is going to act on that wire? In this case, it's going to be pushed into the board. So if I were to hold that wire, it would be like a bow. It would be bowed, and I would actually feel this tension. Now, if we were all here together in the room, I would set this up and we would all grab the wire and feel the tension, just because it's pretty interesting. But I'll just demonstrate it for you. So in this case, so here, force on the wire is going to be into the board, okay, into the whiteboard. That's the idea. But you'll know, so once again, we have electricity, we have magnets, they're completely separate, but now we find that if you have an electric current and a magnetic field, there's a force that results. So let me see if I can set this up and make it look like something. So I'm going to wheel this big old magnet into place. And I'll control that in a moment. See what we can see through this camera. And here I have a device that's going to give me a current. I'll throw this big old switch and I'll get a current. I'll show you in a moment. Yeah, that'll work. Okay, so here's what we would do together and actually feel that I'm just going to have to indicate to you. Okay, here we are. Here's the idea. This machine here, this device, is allowing me to have a current going through this wire, when I flick this, when I close this switch, I'll actually have a current in this wire. Right now, there's no current in the wire, and there's no effect with the magnet, okay? And I'm holding it between the magnet, just like in our picture, basically, okay? So, if I close the switch, I get a current, and immediately, you can see there's actually a very strong, interesting tension in the wire, okay? You can see it being flicked from side to side. So that's that tension I was talking about. So that's out of the board, so to speak, towards you guys. If I reverse the direction of the current just by taking this thing here out of the board, pardon me, and this one here would have been what we're calling into the board, okay, towards, you see how it's bowed. Presumably you can see it. I'll put it in a little profile, and we'll see that again, right? So it's got that arc. If I reverse the direction, the arc is towards you guys. Okay, so there's the important, very important force on a current carrying wire. Okay, I'm going to call that a success. We'll see later if it really was. So we can get rid of this for the moment. And that was that law that we were interested in. The magnetic field acts on an electric current. That's the force law. And there's a lot more to be said. You might want to look this up too and see if you can get some interesting pictures of that. So that's point 3. I'm going to have to erase the board and move on. The next one, so electricity, magnetism, finally the link between the two. And now the next one is another link between electricity and magnetism. So my 4th point in these laws of electricity and magnetism is that an electric current creates a magnetic field. So here's a magnetic field, or here's a magnet that'll create a magnetic field, and I showed you with the compass needles the other day. But now I'm saying an electric current creates a magnetic field. Or produces, how about that? Electric current produces a magnetic field. Easier to write B. Okay. Now, one thing you'll look up is Ampere's law. You can get some good images on this, but I will explain a couple of examples. The first example is if you have a current in this direction. So imagine we have a wire and a current in that direction, I. The magnetic field produced by this is a bunch of concentric circles. Okay. Like that. So this is a long straight wire. And we have the demos to actually show this, but it's a little awkward right now. So you have to take my word for it. I'll give you the top view. If the current is out of the board, so that dot, think of an arrow coming at you. So you're looking down on this wire here. In that case, the magnetic field lines are concentric circles. And we actually can sprinkle, we will have that long straight wire, we can sprinkle some iron filings and they will orient in circles. And remember, what this means is if I put a compass needle here, it's going to go in that direction respectively, okay? So that's Ampere's law. That's the top view. And that is the one important example. The second important example, actually, this is 1 and 2 in parentheses, right? Because our next line is going to be 5. The second example is called a solenoid. And that just means a coil of wires. In fact, it could be a long skinny one, or it could just be a bunch of wires wrapped up in a coil like this. So solenoid, look that up and get some images, but the interesting case is if you have current coming in and then you have this long cylinder wrapped and the current keeps going like that, it's got to be insulated wire. What you're actually going to get is a B field that looks just like the one I erased, okay? So it looks just like the bar magnet, like the dipole. You're going to get this B field, and again, if you put the iron filings there, put the compass needles, iron filings, it's going to show you that B field. So this is really profound that the electric current produces a B field. Because now you can produce magnetic fields of enormous strength by just having a lot of turns of this wire, and you can produce magnetic fields that do what you want them to do. You know, different geometries are available by turning this around, bending it, whereas with a bar magnet, you're just stuck with what you have, okay? So that's the third, or yeah, that's the next law in our list. Electric current produces a B field. Like I said, I have a bunch of those demos. They're not going to work today, but you can find plenty of information on that, and you want images for this as well. Okay? You definitely want images for Ampere's law, and what you'll see is what I'm just showing you here, and you'll print some of those out as well. We don't need any formula for this, okay? So that is the law point 4 on my list here. And the last one that we're going to do today is the one that brings everything together. So let's go ahead and make room for this. And this one's going to take a little more explanation. So I'm just going to write 5 for starters. We have to build this up a bit. Magnetic flux and Faraday's law. Faraday's law. Okay, this is very important. So what is magnetic flux? Flux is just a fancy way of saying flow. So it's the flow, but we're not seeing any fluid flowing here. So I'll give you a little bit of a description of magnetic flux. So we're going to introduce this letter. Phi sub B is equal to the magnetic flux. And what it is the magnetic field times an area. So imagine if the magnetic field were flowing. It is a vector, but there's nothing flowing. But if you imagine it were flowing, and it were flowing through an area. Okay. That's the idea. And this is a perfect example. And I actually prefer this. So here's a coil here, 200 turn field coil is what it's called. It's 200 turns of wire wrapped around in this frame, and you can hook up to the, you can hook wires up to the end. I prefer to actually hand wrap them, because then you see there's nothing fancy going on. Okay, got a bunch of green wire here, wrapped it around many times, and we can hook up wires to the end. That's a coil. What is the flux? The flux is if I hold this up to a magnetic field and the arrows are coming in or going out, or passing through in one or the other direction. That's the flux. So let's add a little bit of picture to this. So example, you're gonna have to draw this. So just as I said, I just wrap a bunch of wires, or a wire. So I've got many, many turns here, like that. Okay. Now the flux would be if there is a B field, because I'm going to use red for the B field this time. If there is a B field that's going through here. So imagine, now that we know that this is just this, I'll use this example. Imagine that this is like a window and it's facing a breeze, and then a breeze would flow through here, okay? Instead of a breeze, which is a fluid flow, imagine that we just have those magnetic arrows pointing at us. The way I can change that flux is just to turn this to the side, and now they just blow right by it. They don't go through it, okay? So we have a flux, but just by changing the orientation, we can have a changing flux. And that's what's really important in this. So magnetic flux is Faraday's law. Example, so I'll write here, imagine B field vectors. Imagine those B field vectors flowing through this window, okay? Flowing, I'll put flowing in scare quotes through the open loop. Okay. Flux. And again, you just look up Faraday's law, you'll find all manner of information and hopefully some pictures that help out understanding that. So that's the magnetic flux. Now, how about I bring this back into play? So here's our giant magnet. Let's see how that looks. Good enough. So here's our magnet, and the idea is that I could hold this in between, well, not this one yet. I could hold this loop in between, and there is a flux. Okay, that's the idea of what we're doing. Now what I have, I'm going to pull that giant magnet away. I can do the same thing without that big contraption. I can say, well, this is a magnet with vectors coming out. Can't see them, but they're flowing through, okay? Now, Faraday's law is very interesting. I'm going to write Faraday's law down. Faraday's law says that you're going to get a voltage just out of that magnet and the coil. You're going to get a voltage under certain circumstances. This here is a galvanometer. It's going to actually measure voltage or current. And so what I have here, I have this coil hooked up to this galvanometer here, and just by moving this in the presence of a magnet, we're going to see the needle move, and it's pretty sensitive, so we shouldn't have any problem. So first of all, I'll just lay this on the table, and I'll approach it from above, and the needle moved. It's going to come to rest. So notice when there's no motion, so the magnet's in there, it wasn't just the flux, it was the change of flux. And I'm going to pull this out, and the needle went to the other side. So once again, if I bring this in, needle goes to one side, and if I remove it, needle goes to the other side. Other things I could do would be to have this thing standing here, okay? Drop it on, pull it back off. I could also, let's see if we can turn it. We could have it here and turn it, That's not going to be as strong of an effect. That's all right. In principle, any change of flux whatsoever will cause this needle to go one side or the other. Now, the reason I drew attention to the two directions of the needle, because one direction is one positive voltage, the other direction would be a negative voltage. If the needle goes back and forth, we have what's called an alternating voltage, giving rise to an alternating current. So now I'm going to write down Faraday's law, and that is that this voltage, they usually use a different letter, but I'm going to stick with our delta V. Delta V is equal to N delta phi sub B divided by delta T. Okay, this is a derivative type of thing, but we don't have to know calculus to talk about it. So I'll frame this in a red box, and then we'll have a look at what this means. This we know is a voltage, okay? We've talked about delta V, that's our voltage. This N here is the number of turns, okay? So just the number of turns, here's quite a few. So number of turns in the coil, okay? So you can see, if I have more turns, I have more voltage. This delta phi over delta T, that's the change of the flux with respect to time. If the flux doesn't change, we get nothing. If the flux does change, we get a voltage. So this is the key to large-scale power generation with electricity. We don't use a battery, we don't use a capacitor. We use some giant coils, giant magnets, which are actually electromagnets, and we spin the coil. You spin the coil, you get the change in flux, and you get that voltage, and then you're on, then you're doing alternating current. Alternating voltage, alternating current. So this here, in fact, you can imagine this B field and spinning this coil and getting this alternating voltage, and the alternating aspect of it was this needle going back and forth. So let's call this production of alternating voltage and therefore also current. And that's why you talk about DC versus AC. DC is direct current, AC is alternating current. So alternating, very, very important. AC. Okay, let me check what we're doing time-wise here. Perfect. So now that we have this, let's just look at a little more applications on this. And then I want you guys to look up enough of these things to really, fill out your book and have it all make sense. So we've got the magnetic flux, that's that flow, got some, pretty much all these things you can use as vocabularies to search out some good material for this. This one is absolutely key. And you can imagine now turning the handle of a generator, okay? You're turning the handle. What it's doing is it's either spinning your loop or it's spinning your magnet. Say it's spinning your loop and the magnet's fixed. And spinning that, and depending upon the number of turns, you're getting your voltage. There's your generator. Okay? So generation works that way. Now here's the thing. If I want to hook this up to some 1,000-watt motor, where's the 1,000 watts coming from? I'm turning this handle. It doesn't seem like it's hard for me to spin this loop, and this is what we really have to experience together, and we're not. when you crank the handle of a generator, which is just this idea, and it produces that voltage and you hook it up to a device, the instant you turn that device on, you feel a strong resistance. Resistance to turning it, and it turns out you have to put those 1,000 watts in by hand in order for the delta V and the current and the whole load downstream to actually function. So that's one of our important demonstrations that we can't do together, is actually to turn a hand crank generator and turn devices on and off and feel that resistance. Be that as it may, we're pretty much complete right here, okay? So what I'm going to do is write two things. Here, I'll make a little box that I can write in. The first thing is homework. We want images for all of these things. Spread them out nicely so that you get that logical flow of how things build up. So all the vocabularies are up here. So we want to get some images, and then I'll write here next. We'll actually do a little bit more demonstration on generator, motor, and transformer. And especially, I want to show you a little motor that's completely transparent, so that we could possibly even build one at home, so that we can see all of these laws in action. So that's my next thing. Next hour that we meet, we'll list these laws again and then see them in action with generators, motors, and transformers. At which point we know everything, right? So, enjoy this. It's a very quick run through that subject, but these are the major points, and we'll see you next week.